Alright, hell yeah. So we have dynamics, and what we're going to do is we're going to set up this problem, just using some lines and a protractor, and we're actually going to get an answer pretty quick. So it says, hey, this thing, both of these kind of slide down, and this angle increases. Now this is a pivot right here, so I mean these bars could be totally perpendicular, but that would be the final motion. And the problem says is that this is going to be a constant speed coming in. And then the other way to visualize this problem, like take it to the extreme, make these like 10 feet. If this is like 1 foot, just make them like 10 feet long, and then you can see that angle would be real shallow. And then as this is approaching with the velocity, it's going to be real shallow, even until it gets to here. And then right here it's at a 30-degree angle, but that last foot is going to go 30 to 90. So you're going to get all of your, the change in this angle per time is going to be the speed that this angle is doing this. So like if it was 10 feet out there, it's not doing that at all. You know what I mean? It's maybe going a few degrees a second, but then maybe this travels 1 foot a second, and so in this second you're actually traveling 60 degrees in a second. So that would be the angular speed. Now we have to work in radians, so that's the other thing. 30 degrees is a half a radian. Just keep in mind that a circle, here's the radius, you measure that, you cut it with a string, you drape it around the circle, you get about to there. That's the definition of 1 radian. It's about 60 degrees. And so there's going to be, sorry about that, there's going to be, did a real bad job, but 6 of those segments, 2 pi segments in a circle. So even right here we could be like, hey, that's 30 degrees, so that's 0.5 radians. That means that 30, 60, 90, so 0.5, 0.5, 0.5. So in 90 degrees, you get 1.5 radians. Duh, that's pi radians, 1.57. Anyway, so if this thing's going from 0.5 radians all the way to 1.5, we would have a change of 1 radian in 1 second. Okay, hell yeah. So that's just kind of the visualization of the problem. And now we're going to go into how do you actually set this up. So because this problem had no numbers, and they want to find the angular acceleration of this bar, which this is fixed right here. This AD is always vertical. And so this change in the angle will be the angular rotation, the angular speed of this bar AB. And we're going to find the angular acceleration as well. So anyway, so I just went for it, you know what I mean? I put my point, this is the fixed point, D right here, and I just went up to do a 30-degree angle to start, so that's going to be this point. And then I just said, well, maybe in a second it's going to get to here. And I just kind of measured that out. I was like, hey, that's about 50.8 millimeters per second, so this thing is going to go 0, 1. So that's going to be the speed of it. We're going to have an angle that goes from 30 to 49.5. So that's the first thing I did. I just wanted to get a feel for it, So we're going to have a change in angle of about 50 to 30, that's about 20. So we're going to have about 20 degrees. And what did we say that was in radians? 30 degrees is 0.5. I don't know, so just like 0.4 radians per second. So maybe that's the angular speed. And that's kind of what I did right here, and we got this 0.34 radians per second. But see how I can just do it mentally, even before even doing the equation. But the equation for this is like, hey, we found the angle at some time later, after 1 second, and then the initial angle of 30. So that change in angle from 49.5 minus 30, divided by that 1 second, that's going to be degrees per second, but we need to convert that to radians. And so if we have this full circle, we're going to have 2 pi radians in a circle, or divide by 180, multiply by pi, and degrees cancel, and then you're left with radians. Okay, so then what we do is we make the problem just a little bit tighter. So I'm just going to say this is the initial position. beforehand we're going to be up 10 millimeters, and then after we're going to be down 10 millimeters. So I measured the angle there. We're going to have a 27.9, and then after 30 it's going to go to 33. And so the change in angle is going to be, we're always having a positive change. So the bigger number minus the last number, which was smaller, divided by the time. Now the time, you know, if I said we were going 50.8 millimeters per second, we only changed 10 millimeters. So 10 divided by 50, what's that? 10 divided by 100 is 0.1, so this is going to be about 0.2 seconds. So we're going to have that degrees divided by 0.2 seconds. That's going to be degrees per second changed to radians, and we get this. So we do the same thing for that second angle, and we get that. We can average them and be like, okay, the average radian, the average speed is going to be 0.226 radians per second. So we improve our guess. We just know this is going to be way better, but if there was a huge discrepancy of orders of magnitude of more than 10 or 100, you know, we would maybe spot that error. Okay, so now that we have the velocity, we have the velocity before and the velocity after, and that's what we averaged. So now we're going to take the change in that velocity, which is just going to be this minus that, divided by that 0.2 seconds, and hell yeah, so that's going to be, you know, 0.405 radians per second. Answer in the back of the book is right here. They do just straight differentiation, and that's what I'm going to get to, not in this video, but probably in other videos. This video is just showing you the setup. So we were pretty accurate there. We're pretty off on the acceleration, but that's totally fine. I don't, because you have to, the difference in measuring these angles between 27.9 and 33, like the tenths of an angle are what's driving this acceleration term. So if my error, it's because I can't just measure very accurately tenths of angles. Because see how this is pretty, well, and then, so I do it one more time. I'm just like, well, let's try to get a better guess. And the issue I was running into is on this one, you know, measuring these angles, I could only line up my protractor on this side. So what I did is I made sure I could line up my protractor on both sides of this grid paper and then just kind of get more precise lines. And then so I set up the problem again. I chose my velocity to be 50 millimeters a second. Each two of these grids is 10, so we're going to go 1, 2, 3, 4, 5. So that's the speed of it, 0, 1. So it's going pretty slow, but then it's opening up at that angle. So I did a better job at measuring the angles. We have an initial angle of 30. Prior to that, it's 26.9. After that, it's 33.4. I'm just going to say we're going this speed. So then the time of going 10 millimeters is going to be 10 divided by 50 millimeters per second. Second pops upstairs, and you get that 0.2. So kind of the same thing, you know what I mean? We can kind of just dust this over faster. So it's the 30 minus that initial angle, you know, prior to 30, and divided by 0.2 seconds, change to radians. And so here's the exact answer in the back of the book, and then here's our answer. So we're getting closer there. The average is even closer because we got those two values for our velocity. Now I guess I will point out that in another video I did, you know, how a distance can change. So let's say maybe the distance, like some point on a mechanism is here, and then a little time later it's going to be here, and then a little time later it's going to be here. Well, you can see that, hey, it went 5 this way, it went 6 this way. It went half up this way, but now it went 3 up that way. So you have a change in velocity. So you have a velocity here, change in position, change in time. Maybe this is 1 second. This is also 1 second. And so you can see that we have an increase in velocity and increase in velocity in both directions. And so we have, because we have a change in velocity, we'll have an acceleration in that direction and an acceleration in that direction. Same thing with angles. So if we have an angle and that angle is increasing, cool, we're going to have a positive angular velocity, but let's say it's increasing but then kind of slowing down. So we're going to have like a, but this one is doing the opposite. It's increasing, but then it's also speeding up, and we've already talked about that, how if it's 10 feet out, sure, it's increasing, but it's just increasing slowly, but it's increasing faster, and so we do have an acceleration, especially right at the end. You can definitely see that. So let's see if we did better between measuring those two angles. And like I said, I mean, we're trying to, these are 1 degree, and we're trying to like figure out where in between it was 26.9, 33.4. So obviously real difficult, because that's what's driving that that change in change in the angular velocity. So we got the angular radians per second is our angular speed, and we have the two values prior or after the 30 degrees, prior to that 30 degrees. We take the difference between them. We still take the same time frame of that 0.2 seconds. And let me explain that, because that's going to be the confusing thing. How if you have a point that's 0.2 seconds that way of 0 and a point 0.2 seconds this way of 0, when you average between those, why wouldn't you use 0.4 seconds or double it? And the reason is that you just know that this average velocity you're getting is hopefully somewhere dead center. You know what I mean? Hey, we're going to be slower here, faster here, and we're trying to find the average. And we're just hoping that's a linear relationship where halfway is going to be where we're basically measuring that value. Same thing here, between 30 degrees and 33.4, it's really like we're measuring halfway in between, and that's where we're going to get that value for that velocity. And so those two, the one prior and the one after, the distance between those, if linear, will still be that 0.2 seconds. That's the only thing that is kind of like a little bit wonky. Now if you use straight differentiation, here is the omega, here's the change in angle, radians per second, and it's a function of, so we'll just end the video. It's going to be a function of this velocity, this distance, and this angle. And so those three things are going to determine what the angular speed is at any point. And then the angular acceleration is going to be a function of those same things. And honestly, angular acceleration is a function of angular speed. It's just that when you derive this and you get like the theta dot term in here, you just take this part of the equation, shove it into here, and then you can get kind of everything just as a function of these parameters. Now these parameters change because well, d is constant. That's the only one that's constant. Well, no, and velocity is constant. But in this equation, theta is going to change. So they want to know that if we always have this constant velocity, if this is always a fixed point, and we take a snapshot of this system at that angle, we're going to be able to find its speed and its acceleration. So we just chose the angle of 30, but from this you could definitely see that if we went down to a 60-degree angle, that angular speed is going to increase, that angular acceleration hella. And if we go to a less angle, you know what I mean, if 30 is 0.5 radians, let's go to 15 degrees, which would be 0.25 radians, and your angular speed is going to be slower, your angular acceleration is going to be slower. Alright, hell yeah. So anyway, that's what I wanted to go over, just how to take a problem. And the reason you would do this is because, you know, deriving these equations, there's so many places to get into errors and just little mechanical things like sign changes, and especially because you're deriving sines and cosines, so you can make sign change errors. And so this just gives you target values to shoot for when you actually get these equations, and then you could throw in 30 degrees. That's what I did, and then I see how these are similar. So we're so my method here of actually just drawing these out is sound, but I know that sound. I'm just showing you this method because you can use that prior to a problem, especially if the answer is not in the back of the book, to kind of double check your answer as you go. Alright, thanks for joining me on this one, and that's a video.